for coming. We heard an excellent colloquium, ITC colloquium by Jason Hunt from the University of Surrey. And he will continue telling us more about the dark matter wake of a galactic bar revealed by multi-channel singular spectral analysis. And after that, we hear from Marbely, Micolta, Calderon from the University of Michigan, right here, who will tell us about where did the rocks go, tracing refractory depletion in planet-forming disks. Then we'll hear from Megan Tillman visiting us from Rutgers. Where is Megan? Over there. Who will tell us about the effects of galactic feedback on the intergalactic medium. And last but not least is our own Devesh Nandal, a new postdoc in our corridor. So welcome Devesh, and anyone interested in discussing with him anything to do with massive star. He's the world expert, so he knows everything about massive stars. And he will speak about the evolution and final fates of supermassive stars, so even more massive than we usually deal with. So we'll start with Jason. Go ahead.
All right, hi everyone. I'm Jason Hunt from the University of Surrey, new lecturer in the UK. And so saw a few of you in the cloaker a minute ago, but this will now be on something completely different, so you're not having a redundant talk, except for the first slide afterwards. But yeah, I'm going to talk about the dark matter wake of a galactic bar. So this is not in the Milky Way, I'm not talking about real observational data, but how we do analysis of simulations with some new tools. So a little bit of perspective. Milky Way structure and dynamics are of course somewhat unknown. We don't have this view, this classic gaseous impression. We know we're a barred spiral galaxy, can't look down upon it. And features such as the parameters of the bar, length, strength, pattern, speed, etc. remain uncertain. We know we're a barred galaxy. And one of the ways that we can explore galaxy evolution is, of course, with simulations. They help us compensate for observational biases. They let us look at scales we cannot observe, so no selection function, no extinction. They let us look at evolution over time, how, for example, the bar will evolve. They let us examine the dynamics of dark matter, which is, of course, invisible, if it exists. And however, they are not ground truth, right? Someone said the phrase, all simulations are wrong, some are useful. That's, of course, the case. But even assuming that it is perfect, that we have a perfect reproduction of the Milky Way, they're also really complex systems. These live, many bodies can lead to chaotic dynamics and evolution that are not immediately apparent to the human eye, and they require new analysis techniques and methods to really take full advantage of these simulations. So this is a gratuitous illustration of a galaxy for my next paper, but it's not the one that we're going to be talking about today. Instead, I'm going to be talking about tool sets from the EXP and BFE collaborations. So this is us here on the left, and EXP is a code library from Martin Weinberg in University of Massachusetts Amherst for doing basis function expansion galaxy simulations, but also analysis toolkits. So the simulation I'm looking at is not a basis function expansion simulation. It's a normal n-body from a tree code, but you can still use basis function expansion to do the analysis. And so this is the galaxy in question, which I'm going to post-process and analyze. It is a pretty bog-standard barred n-body disk galaxy simulation. The disk is fairly stable in the beginning. You'll see the bar start to evolve here. Surface density on the left. Radial velocity quadrupoles, the motion of stars in and out. Vertical position and velocity, almost nothing happens. This bar does not buckle. It doesn't go through a violent buckling event, but it does slowly grow an X shape through vertical resonant excitation. You can see there on the edge-on view on the top right. But yeah, this gets strong over time, larger and stronger than we think the Milky Way bar. So this is not supposed to be a Milky Way analog, just a nice laboratory for exploring bar dynamics in an otherwise relatively well-behaved system. And of course, for simulations, we can also look in the dark matter particles. This is a fully live halo with several hundred million dark matter particles, and you can see a corresponding clear formation of a shadow bar appear in the dark halo. So this is already known, it's not a new discovery, that these things can form depending on your profile and the nature of dark matter. For example, from Mike Peterson back in 2016, they had a whole paper on the shadow bar. But this is now a fixed illustration of the bar evolution over time. The top row is face-on stellar density. Starting from the smooth disk, you grow this large bar. By the end of the simulation, it's wildly too strong for the Milky Way. Milky Way-ish is somewhere around these kind of middle panels, 3 to 4 gig years. And the lower row Bottom left is just dark matter halo density. It's just spherical in the beginning. And then the rest of these panels are the fractional difference in a slice through the z equals 0 plane, showing how that it changes. So there's no dark disk. It's all a spherical component. But over time, the evolution of the bar in the disk starts to both rearrange generally the radial distribution of the dark matter. So blue is underdense, red is overdense. But also you have this strong dark shadow bar thing appearing in the middle, and is effectively the same. It's dark matter particles that are close to planar orbits. You have a spherical system. Some of them happen to be in that axis, though it's a minority. They can still be trapped into the bar in the same inner Lindblad resonance that forms bars in the stars. And I'm not going to go through all the technical details of basis function expansion. I direct you instead to my paper and those of Peterson and Weinberg. But in this, I like to, if you're familiar with basis function expansion, it's a reasonably common technique in the galactic community to do spherical expansion using Hernquist's SCF field theory. But if you don't know that, you can kind of think of it in the way that, in the same way you can use Fourier analysis to decompose some time series into a superposition of sine and cosine waves, you can actually decompose a very large 3D particle-based galaxy simulation into a superposition of a lot of weighted basis functions. And so we can do a spherical basis for the spherical halo. The lowest order function is kind of conditioned on the general density profile, and then there are modifiers on top of that. And we do a cylindrical basis for the disk. Again, I won't go through all this, but the details are in the paper and on the EXP library website on the bottom. And when you do this expansion, you get out coefficients that weight these basis functions, which encode the evolution of dynamics over time. So you have here on the left the evolution of the m equals 2 disk coefficients. So again, you can think of this in the terms of like if Fourier, if you're doing an m equals 2, the bar is an m equals 2 structure, is that kind of symmetry. And you see the amplitude of these m equals 2 functions increase over time. This is when the bar starts to form visually, and it goes up to some kind of steady state. So the intuition there is fine. If you look in the log one, you have an exponential growth in the beginning and then close to steady state. Don't worry about the bulge for this talk because it's a short version, but for the halo, you see some kind of corresponding growth in the L equals 2, M equals 2 spherical harmonics. L equals 2 means vertically squashed. So you're getting the more diskier part of the halo. Again, it's not a dark disk, it's just the part of the halo that happens to be on those orbits. And again, you see this kind of, just by eye, there's a correlating growth. That kind of structure we saw in the plot is still there. You get pattern speeds out of this. So the change in phase between the functions here gives you the pattern speed evolution. So you see the bar slow down over time through dynamical friction interaction of the halo. That's fine. Halo, you also see the same thing in these L equals 2, M equals 2 coefficients. If you plot them over top of each other, it's the same pattern. It appears to be consistent. The interesting, nice thing here is like the disk is basically the same until it couples to the halo. The bar pattern speed is basically the same when it's growing until it couples to the halo, and then they decrease together. The halo is all noise until it couples to the bar, so you see the coupled signatures. But this is noisy. There are a lot of dynamics encoded in M equals 2, right? You can have spiral patterns, you can have other things going on the disk, and this is where the second half of this comes in, using multi-channel singular spectral analysis to do time series analysis of these coefficient series. And this is where you can start to learn about the dynamics. So this is mainly an advert for this. Again, I won't go through the maths of MSSA. It's originally done from a financial time series, but it's basically a signal analysis package to pull out signals from noisy data. And so we can cross-correlate the time series of our weighted basis functions to correlate specifically signals in the disk or halo that are the same, that are explicitly dynamically coupled. And so we're going to use it for. So we're going to correlate the series we just looked at, the disk M equals 2, corresponding broadly to bar-ish stuff, and the halo L equals 2, M equals 2, so squashed bar-ish stuff. And this is the technical plot that I won't spend too much time on, but basically you get PCA style analysis out, you get principal components. We spend some time grouping them into distinct dynamical regimes. I will not go through that because there's only 10 minutes. I talk about how you do the grouping in the paper, but basically it breaks up the time series into different regimes of the bar growth, where the dominant PCs are that late time super strong bar, and then going down to the earlier PCs when you had the bar formation. But these are all explicitly coupled in the disk and the halo together. So we've lost anything that only occurs in one or the other. From that, you can reconstruct the contribution of these principal components to the original coefficient time series. And again, you see the same thing here where some of the PCs give you that early bar exponential growth phase, then the intermediate phases, and at the end, the most dominant PCs are that super strong late stage bar. And you add them all back up together and you get your kind of original coefficient time series, but losing some of the noise, that's fine. And so from there, you can project these back out into the density fields for both the stellar disk and for the dark matter halo. And so this is one of the plots I really like. You have in the disk, this is just the bar quadrupole, as you would expect, m equals 2 symmetry. Now, real bars are made up of more than just a perfect m equals 2 quadrupole, but for the simplicity here, that's just the bit that we're looking at. These left to right panels are generally increasing in time, so younger, weaker bar at the start, a stronger bar towards the end, and you see the same corresponding quadrupole pattern appearing in the dark halo. And so when I say the same, it's not exactly the same. You can see phase lag in the halo response as the dark matter has a trailing wake that will spiral outwards from the kind of more rigid shadow bar in the middle. And then you can do effectively summary statistics on these explicitly correlated, dynamically coupled features in the disk and halo. So these different groups that I showed in these panels here, orange, green, blue, red, gray is everything. You see the coefficient amplitude split by phase. You have exponential growth phase, linear growth phase, and then a couple of distinct steady state phases that split with the analysis, whereas by eye, perhaps we would have said they were the same. You can see the pattern speed, it slows over time, that's fine. It becomes interesting when you look at like relative growth rates. Almost done, this is the final slide. Relative growth rates. So disk grows faster than the halo, halo responds, catches up, and then there's a couple of different phases. They look minor here in the relative growth rates. If you look at the phase lag, as the bar is growing, the phase lag is getting larger, and then once it saturates, the dark matter wake starts to pull back into the phase, into phase with the bar as this goes back down again. Pattern speed decreases faster when you have the larger lag because of the torque on the bar. So this is all qualitative consistent with evolution that we already know. So I'm not saying that we have revolutionized newly discovered dynamics, but the combination of basis function MSSA is a really nice toolkit to pull out explicitly coupled dynamics. And so this is effectively an advert for that machinery. Paper was submitted recently on arXiv if anyone wants to read more. Thanks very much.
So Jason, it's a bit difficult to see the forest from the trees, from technicalities, but you would expect the bar to behave like a blender that basically flattens the inner cusp of the dark matter profile, and I haven't seen, it wasn't clear to me if that's what you see here. And by the way, 50 years ago, the lack of bars was argued as evidence for dark matter, by Jim Peebles and Jerry Osraker back then. But so what is the ultimate effect of the blender on the dark matter?
So in this instance, I was looking not so much at the global change to the halo, that you can see it a little bit from this early plot is actually the only one that really addresses this question, where you see the general change in density that is happening, as you were saying, there is a flattening in the inner part as the halo goes outwards. So I was focusing on the quadrupolar structure, but that is going on. If you wanted to examine that with the MSSA and BFE machinery, I would need to plug in different basis function time series into the MSSA in order to do the explicit correlation. So that test could be done. It's not illustrated in my slides here. But yeah, we could absolutely do the same correlation. You'd take the same bar coefficient series, but with a different spherical harmonic order for the halo. It'd be an interesting thing to look at.
Please.
So I've thought of the slowing down of the stellar bar due to sort of an offset in the angle between the stellar bar and the dark matter bar, and that's what's pulling it back. Do you find that here, or is it a different dynamical friction stuff happening?
It is the phase angle. However, there is a trapped component that matches the phase angle, because you can trap some of the dark matter particles that are on disky orbits in the same ALR shape orbits that make up the stellar bar, like that you can trap those. But then you have the larger trailing wake outside that ILR trapped region that gives you the torque that slows down the bar, and as you have the larger phase, you have the larger torque, so that the intuition is the same. But there is a small trapped component that doesn't have an explicit phase lag. Yeah.
Does the halo rotate initially, and is there a spin halo spin makes it?
This one starts from a net non-rotation halo. That would be something worth looking at, the effect of the halo spin. There are a bunch of studies that look at bar evolution as a function of halo spin, and so that's one of the future projects for someone else in the collaboration is to do this as a more systematic study of halo properties. It probably won't be my task. I'm happy to hand this over to students now. But yeah.
Any other questions? If not, let's think. Oh.
Do you know what triggers Clark property here, or is it like numerical, or?
I think it's numerical noise. This one is pretty stable. It's deliberately designed to be warm and more stable, higher numeric temperature, etc. But yeah, eventually it's just numerical noise. Yeah.
Thank you, Jason.
Thank you.
Okay. Yes. Okay, great. Thank you so much. I'm Marbely Micolta. I'm a grad student in University of Michigan, and I'm working with Nuria Calvet. And today I'm going to talk to you about rocky material, or where did the rocky material go in planet-forming disk, also called protoplanetary disk. And just as a brief introduction, just by consequence of angular momentum conservation, when stars form, the material will get flattened out into a disk, and this is where planets are formed. And I will be talking about planets or disks around T Tauri stars, which are young low-mass stars. So these are all happening around stars that are lower mass, or the higher end is the solar mass, which is a very interesting topic because this is where most of exoplanets that we have found are, around these stars. And the way that these are, like, this is a schematic of the disk. So they're made of gas and dust. And then the dust is settled into the midplane. So the bigger the dust, the more towards the midplane it is. And then it will move inwards towards the star. And then as it moves, the disk will get hotter. The closer that you are to the star, the hotter it is. And then the more volatile, icy material will sublimate, evaporate, come back to the gas. So that's what I'm trying to represent with the different colors. So you start with very dark disk gas environment, and then as soon as the ices start evaporating, then your disk chemistry change in the gas. And then the interesting part is that it gets very, very chemistry dynamically interesting in the inner 10IU, which is also where most exoplanets are detected. And this can have a lot of implications for exoplanet composition. But however, what I'm here to tell you is that we should care about rocky material, because to form an exoplanet, you first need to form the core rocky material, and we need to understand what this material is doing in order to understand anything else about exoplanets. And an interesting thing about rocky material is that it will always be locked in this solid state. So you cannot lose it by anything else but dust trapping processes, unless you reach regions about 0.1 AU, very close to the star, when then you reach the 1600 Kelvin that you need to evaporate them, and then you get to like what I call the innermost gas disk. Everything has turned into the gas. It's very refractory material will be in the gas, and then we will funnel into the star doing the magnetospheric accretion flows. So looking at this inner region is very important because it can tell us a lot about the pebble floods, which it's very important for formation of super Earths and etc. models. There is a lot of ways that we characterize disk. I think one of the most picturesque ones is when you go to the millimeter wavelengths with things with ALMA. And this is just showing gas versus dust. And this is all the same disk. So that just shows you how widely different tracers can be. And then something that we are very excited now is that we have GWST, and that can tell you a lot of the gas in the innermost regions. So with ALMA, we see the outer parts, beyond 10 AU in most cases. With GWST, we can start seeing the inner 10 AU, again, where the most planets are found, and then we're more interested in characterizing what is actually happening. And then we have, with optical on ground-based HST, we can actually access the innermost inside 0.1 AU. And this is a very rich spectra of a completely typical T-Tauri star. So a few things I want to highlight here is when we look at optical spectra, we're basically looking at the innermost gas and the accretion flows. This UV excess that you can see here is caused by the accretion, the excess luminosity when the accretion material reaches the star. And that just tells you how much mass is actively reaching the star, how much material is actually making it to the star. And I will refer to this as a mass accretion rate. And then in these flows, you also have emission of a lot of lines, especially the hydrogen-Balmer lines, but you also have a lot of refractory lines that are formed in the accretion flows. So this is great because we can use the lines to trace what is actually the content of material, of refractory material that is actually making to the star. So that's how I'm going to start. I'm going to focus on only these two methods in this talk. So as my title suggested, we have a problem with rocky material. My title was, where do the rocks go? So we actually find that rocky material tends not to be in the star. So I'm showing you two spectra of two very similar stars. So the log M is accretion rate, again, how much material is falling into a star. Essentially the same. Same spectral type, that just means that basically same temperature, effective temperature of the star. They're both from the same cloud forming region, so they have the same initial conditions. But you can see a very wide difference in behavior of the calcium lines, so these two columns, versus the hydrogen line. Hydrogen traces gas. It's always going to be in the gas. As you can see, they have very similar behavior in the sense they have very strong lines, and they have similar fluxes. So we have a lot of material falling in. It's just that for this bottom one, for T28, somehow we do not have refractory in that gas that is falling in. And we actually find that this behavior in some systems, and by some, I mean a lot of them. This is showing, for example, about 70 stars. About 60% of them had a high level of refractory depletion. So we cannot find refractory material in the accretion flows, which means that there is no refractory material passing the sublimation point. They must be somehow, either we already lost it all, which is very troubling for planet formation in these star-forming regions because it's about 2-3 million years old. That means that we will need to start forming planets real fast, or it gets trapped outside, which is a very interesting probe, because if it gets trapped, then it's probably to some extent related to planet formation happening. So what I want to talk is how a broader picture of this disk can actually tell us about what's happening with the disk. So I have a case study of BP Tau, which is a very typical T-Tauri stars, except that even your typical T-Tauri star is very interesting. Mm-hmm. It was thought to be not structured. There might be some structure. And I'm showing you here how the emission lines look optical versus UV. So again, very strong H-alpha, very weak calcium. So that already tells us something. And now I'm going to add magnesium into the mix. So what I'm showing here is the modeling of the emission lines with the magnetospheric accretion models. You can ask me about that if you want later. But the interesting part here is that we record about 1% and 5% solar abundance for these elements. Solar abundance is the expected value for all nearby star-forming regions. This is significantly lower to the point it cannot be explained by anything else. Either you lost it all in some massive accretion process, or you are trapping it outside. So this is a very telling, again, most typical T-Tauri star, very depleted. So we end up going further out to the mid-infrared wavelengths, again, the other method I'm going to discuss today. And the way we do it is like modeling the spectral energy distribution, or the SED of the star. So by doing this and using JWST or IRS, I'm showing here just a modeling with IRS as Spitzer, you can model, we focus on the continuum. Again, JWST is very beautiful, but the most exciting part about JWST spectra is the gas lines. I want the continuum because this is where all the information about the rocky silicate dust is. And the way we do this with forward modeling, we want to fit every single different wiggle to get the composition of the dust. So here I show you three very common meteoritic material in our own solar system. So enstatite, phyalite, and forsterite. I want to highlight here the red and blue. So phyalite and forsterite are the same type of silicate. The only difference is if forsterite is 100% magnesium and phyalite is 100% iron. So just use the composition can give you a very significant difference in where and how the wavelength peak, and this is what we're trying to do with our modeling. Beyond that, it can actually tell you about the structure of the disk. And for BP tau, we actually recover an optically thin region. That just means that there is a gap, but the gap is actually filled with dust. I'm about to end. So it's, again, very typical, but it has a gap. And this is a very powerful tool because there is a lot of these on systems where we cannot get the structure of the 10AU just by resolution limits. And this is something that can provide us that information. And then my last slide, when we put all of it together, we can actually reconstruct the gradient of magnesium abundance happening throughout the disk. So we find magnesium rich in the outer parts, and then when we make it to the inner parts, it's magnesium poor, which is correlated with what we find in the accretion flows. And the change in composition seems to happen in the gap, which is very interesting. And I have, unfortunately, no explanation about why. We need more detailed modeling of everything. But again, I'll leave you with my summary slide. But basically, we need wavelength multi-species analysis about rocky material to be able to constrain dust drift and dust trapping models, which will lend us to constrain exoplanet formation. Thank you.
Marbely, this is very interesting because we do see, it's just the beginning now, we do see interstellar objects and they seem to require like tens of Earth masses per star.
Yes.
To be ejected. So it's possible that those protoplanetary disks are losing a lot of rocks.
Yes, so there is a competition, let me see if I have a, here. There is a competition between dust drift and dust trap, right? So, which is why I want to do a bigger sample search detail modeling, because if the dust drift, which is how fast the material is moving inward, is very efficient, you will accrete all the material very fast, and you will be left with nothing to form planets. But if you trap it, there is multiple ways you can form a pressure bump in a disk. However, if you have a pressure bump, which by whatever mechanism, you'll be accumulating dust, and that is just perfect conditions for planet forming, for planet formation to begin in the disk. So what I actually want to do is here. So Orion 1b is one of the oldest star-forming regions. It's older than 5 million years, and we can see that it's mostly all depleted, so that hints to dust drift effects. But we also see a lot of depletion, but also no depletion in the younger ones. So it's most likely a combination of the two things that we're seeing, and that's why I want to do the SED modeling to be able to say, okay, is there any trend? Is there any trend within the elements, within the changes in composition? Is it related to structures, how big the structures are? To be able to say how leaky they are, how effective they're trapping, and which will ultimately tell us about the pebble floods. And that's important for super Earth formation mechanisms.
Excuse me, you just said structure, and that's what my question is about.
Yes.
So So a lot of these disks have more than one gap?
Yes.
And so I'm just curious, what happens to your story when there's more than one gap?
So when it's more than one gap, there is actually a paper by Melissa McClure about TWE Hydra. What you're happening is that you will be trapping in each one, and that will produce more than one, more than one pressure bomb. So you will have a higher level of depletion at the end because you have multiple traps and it gets along the way. However, a trap does not just fully stop the drift of material. We have seen that traps tend to be very leaky, and we see with BP Tau too. We found a lot of material. Essentially, all the red, which is this whole 10 micron silicate feature, it all's coming from the gap. So they're very leaky. There is material there. It's just that if you have multiple, then it will get trapped along the way. And in that sense, we will need to combine ALMA, our millimeter longer wavelengths outer this with this kind of modeling, because it's very useful up to 10 IU. But then after, you really don't have information about the outer disk. We can say the outer wall, in this case, because it's about 8 AU. So we can get this, about 30 micron information comes from there. But outer this information must come from submillimeter wavelengths.
Since the answers were long, we just have time for one more question. Yeah, please.
Yeah, very quick. So precisely outside of 10 AU,
Yeah.
ALMA shows you that there's a lot of dust still in the disk.
Yeah.
So is this realistic to have all the refractory material, accreted onto the star and still have a significant dust population?
Yes,
Yeah,
so the dust disks are smaller than gas disks, that's true. We have seen there is a lot of ALMA data about dust, so you still have, for example, for BP Tau it goes up to 40 AU, 50 AU. So there is still significant dust there. It is true that older disks are more dissipated. We have about 75% of the disks are dissipated by 5 million years. So it's something that happens quick. But the survivors of that process are there, and you can find disks about 30 million years that still have a significant dust mass. So material gets trapped outside. How, we don't really know. Yep.
Okay. Hi, everybody. My name is Megan Tillman. I'm a PhD candidate at Rutgers University. I work with Blakesley Burkhart, and we look at the impact of galactic feedback, specifically AGN feedback, on the intergalactic medium. So just as some motivation why you should care about this topic, we're going to talk specifically about feedback from supermassive black holes. And we have to recognize that constraining this type of feedback is a multi-scale problem, because you have to think about mechanisms as low as sub-parsecs, on ranges as small as sub-parsec scales, up to megaparsec scales, right? Because you have to think about the accretion disk of the black hole, how the matter falls onto that, and then how it's ejected. And then you have to think about these relativistic jets that are shot out from these black holes, how far they can reach. They can heat the intergalactic medium to high temperatures. And this is really tricky because different AGN feedback models can produce very similar galaxy statistics, which is usually what we constrain our cosmological hydrodynamic simulations on. But they, as you can see, produce very different boxes. The temperature in the IGM in these 5 simulations are very different. And so it really emphasizes that we need to be constraining these feedback models to larger scale statistics in order to completely understand what is going on. So we're talking about group and cluster statistics, we're talking about the circumgalactic medium, we're talking about the intergalactic medium. So how I study the intergalactic medium is I look at the Lyman alpha forest. So the Lyman alpha forest is a series of Lyman alpha hydrogen absorption lines that we see in the spectra of quasars, because as this light travels through the intervening material to us at Earth, it is absorbed by various neutral hydrogen structures, and that populates various Lyman alpha absorption lines that are trees in the forest that is the Lyman alpha forest. And this helps us study gas that we otherwise wouldn't be able to see because the IgM is very dim, right? We can't see it in emission. So I study this in simulations, and at higher redshifts, Z of 2 and up, our cosmological simulations match observations of the Lyman alpha forest very well. So on the left here, I have 2 plots of the Lyman alpha forest column density distribution function. These lines are the simulation data, and the points are the observations. And you can see that the simulations match very well with just lambda CDM and the assumption of a spatially uniform ionizing background. So very simple physics, great match to observations. This has been the case for a while. So the story gets interesting when we go to lower redshifts. So I'm talking about now redshifts below 1.8. So first of all, we need space-based telescopes to observe the Lyman alpha forest at this redshift because of the wavelength that it's at. So this means basically Hubble is all we got to observe the Lyman alpha forest here, and its capabilities are pretty limited. So we only have observational data from Z of 0 to up to about 0.4. And then from Z of 0.5 to 1.8, we have this blind spot in our observations where we don't know what's happening in the Lyman alpha forest. Furthermore, simulations consistently struggle to match observations that we do have at low redshifts. So this is a problem that we need to address in our simulations, and it's likely due to a misunderstanding of how heating mechanisms work and how they're being modeled in our simulations. So we specifically look at AGN feedback and how differences in AGN feedback models might impact this specific problem. So for example, here I have 2 temperature projection plots from the SIMBA simulations. The left is one with stellar feedback only, and the right is when you add in AGN feedback. And you can see the huge difference that adding in that AGN feedback makes on the temperature in the IgM. And this comes from these bipolar jets that SIMBA models in their simulations that heat gas out to megaparsec scales. So I'm going to show one result because it's a 10-minute talk. And so I will be showing you the 1D transmitted flux power spectrum from the Lyman alpha forest in the SIMBA simulations. So the flux power spectrum is basically how much variance do we see in the Lyman alpha forest flux on different physical scales. And because we're in Fourier space, we are looking at large physical scales at the small k end. And then at the high k end, we're looking at small physical scales. And for ease of comparison, I'm going to be showing you ratios. So we're going to be looking at how the relative change in the power spectrum when we vary different AGN feedback models. So I'm going to go one by one because SIMBA has this great set of simulations where they add in the different AGN feedback modes one by one. So it allows us to really isolate the effects due to AGN feedback. So I'm comparing the power spectrum to a simulation with only stellar feedback, and that's that black line there. And I'll explain what the changes in the power spectrum mean physically for the IgM as we go. So first we have a simulation where we add in a radiative feedback mode. And we have an increase in power at the low K end of the flux power spectrum. And this is actually due to the fact that this radiative feedback mode suppresses stellar feedback. And that suppressed stellar feedback actually lets the black hole grow more, which makes its feedback more powerful. So it's this weird interplay between the stellar and the AGN feedback that kind of highlights this problem that we really need to be constraining all of these feedback models together because they have complex interplays in these simulations. And then the really interesting bit is when we add in the AGN jets. These are these bipolar jets that reach out really far into the IgM and heat the box. And you have a huge loss in power, right? Because you're ionizing all of this hydrogen. The IgM is much hotter. And you have additional suppression on the high K end of the power spectrum, right? This is changes changes on small physical scales. So for the Lyman alpha forest, these changes are going to be manifesting in the form of thermal broadening of absorbers, right? So you're broadening the individual absorbers, you're increasing the temperature of these individual absorbers, and that causes additional suppression at the high K end of the power spectrum. And then you have a similar effect when you add in this X-ray mode, but this feedback mode is a more local feedback mode. It impacts largely the galaxy. But again, because of these complex interactions with how these feedback modes and types interact with each other in these simulations, you're still going to see an impact on the Lyman alpha forest. So this was just one redshift, right? Z of 0.1. And if we look at all of the redshifts we have available for observations, and we put those on the plot and compare, we can see that simulations with these AGN jets match the observation quite well. It matches much better than simulations without the AGN jets. And these changes due to AGN feedback are greater than our observational errors. So hypothetically, we could use the Lyman alpha forest to constrain feedback models in simulations. So now we want to look at what happens as we go to higher redshift, right? Because at low redshift, we kind of saw that these effects are pretty dramatic in all of these cases. So when do the effects of AGN feedback become observable? And we don't have observation data in this redshift range, but we can kind of think, okay, if we had observations that were pretty comparable to what we have at lower redshift, we can do a thought experiment of when these effects become observable in the Lyman alpha forest. And we see that they become observable right smack in the middle of this observational blind spot that we have, so right around Z of 1. So this really just emphasizes the need for more observations of the Lyman alpha forest and the need for a next generation space telescope that's going to be able to collect that data. And that will come in the form of the Habitable Worlds Observatory. Yes, it's not just for observing habitable worlds, it's also for observing the IgM and the CGM, and it's a great project and everybody should go look it up. And I'd be happy to talk more about it if anybody is interested. But basically, our conclusions here are that the low redshift Lyman alpha forest can be a powerful diagnostic tool for simulations if we can learn to harness it. So heating by these AGN jets has a dramatic effect on the Lyman alpha forest at redshifts of 1 and below. And this makes the low redshift Lyman alpha forest a candidate for constraining not just AGN feedback, for all galactic feedback models because of how they interact with each other in these simulations. And of course, additional observations at Z less than 0.1 are going to be, or less than 1.8 are going to be vital for this effort. So that's where Habitable Worlds comes in. One day, hopefully its funding won't get cut. And we can do further exploration of these types of variations in AGN feedback models with CAMEL simulations. CAMELS is also a wonderful project if you haven't heard of it. It's basically okay, maybe if somebody wants to ask about CAMELS, I can explain it. But thank you.
Thank you, Megan. We're not that strict. We're not Switzerland. You can take a few extra.
I wrote a tight ship.
Anyway, just a quick question. You looked at the power spectrum of the Lyman alpha forest, but there is another statistic that may give you the signal much more clearly, and that's a cross-correlation between AGN and the Lyman alpha forest. So in other words, you have, like, let's say, DESI or whatever survey of the distribution of AGNs, and then you cross-correlate that with the Lyman alpha forest.
Yeah, I've wanted to take future work in more of the direction of looking at individual observer statistics. So I haven't thought about that exactly, and I would love to talk to you more about that and what that would entail. But we wanted to look a little bit more at how the absorber properties correlate with galaxies themselves. So I guess that would be kind of similar and hopefully give us the same. But that sounds like a powerful metric that we can also include in that. Because these summary statistics kind of wash out sometimes the unique effects of these AGN and stellar feedback.
Yes.
Hey, thank you. So, let's see. SIMBA does really well at moving the gas around, and the baryon power spectrum that it predicts is more in line with kind of weak cleansing and KSE and FRBs. But as you show, the temperature of that gas is really high. So my question is SIMBA already ruled out, constrained against by non-detection of the thermal SE in the IGM, so like stacking on filaments, for example?
I think I saw somebody present results on this recently, and I want to say it might have been ruled out. I don't think SIMBA's the best model. I'm big team, no simulation is right, but we can learn a lot from them. So I'm not diehard SIMBA is correct, but I think it's a good illustration that like these AGN jets are what's going to be impacting the IGM for the most part. But we do want to explore what other type of AGM feedback modes would potentially impact the IGM as well.
Ramesh?
Yeah, very quick. What is X-ray mode feedback? I
Yes.
know the other two, but X-ray I have not heard of.
Yeah, so basically in SIMBA, the X-ray mode, so the jets decouple from the hydrodynamics in the simulation because of the coarse resolution, and they don't want it to blow apart the galaxy. So the jets are not really operating locally. They kind of recouple like right outside the galaxy. So the X-ray mode is added in on top of the jets. It happens when the jets occur to kind of just dump more energy into the galaxy to help with quenching.
It's
So
all still in the radio mode, is it? Or is it also in the quasar mode?
it's just in the quasar mode.
It's only in the quasar.
Yeah, the X-ray mode's only in the quasar mode.
But it also has a jet.
It accompanies the jets.
Accompanies jet.
Yeah.
Okay.
Yeah, but the jet is only 10% of AGN. Right?
Yeah.
So it's a small minority of the
Yeah. It doesn't. Yeah.
Okay, well, last question.
Yeah,
Go ahead.
it's a good question or comment. Habitable World Observatory is like 20 years away at best, if it's funded. But there's a Chinese space station observatory that is going to be launched, I don't know, next year, and they have UV capabilities down to 200 nanometers. Do you know anything of their spectroscopic instruments?
I don't think they have a high enough spectral resolution. I think they looked at this. Because you need a really high, you need like 20 to 30,000, or 20 to 30,000 spectral resolution for blinding off force, unfortunately.
Okay.
Okay, let's thank Mika again.
Right, so hi everyone, I'm Devesh. I'm a new postdoc here at the ITC, and I work on the evolution of massive and supermassive stars. So I'm a stellar evolution guy. You're going to see very boring 1D plots. You just saw wonderful 3D simulations, but please bear with me. I think I have some interesting results to show you, but before that, I'll just quickly show the kind of stars I'm interested in. I'm mainly interested in the physics of rotation, the internal magnetic fields, Taylor-Sproyd dynamo, and mass loss in stars at solar metallicity, but also metal poor stars and POP3 stars in the early universe. And there I'm interested in looking at the nucleosynthetic yields of these stars, and if there's a way we can spot them, perhaps. The thing that I'm going to talk to you about today would be about these crazy supermassive stars, believe it or not. And before I begin, and before you ask me a question, I have a silly question for you. Bear with me with this thought exercise. Imagine you have all the perfect conditions for a star to grow. So in your simulation box, what is the theoretical upper limit a star can have? Given you have all the matter available to accrete onto an object, no radiative feedback, everything. What is the theoretical upper limit on the mass of a star? I'll let you think on that while I talk about these supermassive stars in the first place. And really, as you know, they've been spoken about since the last 60 years, where the idea is to explain the supermassive black hole seed problem. These stars, they produce a heavy seed, so you don't have to grow these seeds via super-Eddington accretion. At sub-Eddington rates, you can use them to explain the black hole mass. But what I want to talk to you about today is, as the title of this thing changed yesterday, is we think we've found the very first chemical signatures of these stars, if you were to believe such a star would exist in the first place. And this really goes back to the work of JWST, and there's been a bunch of galaxies that have been spotted in the high redshift universe where we see, especially this nitrogen over oxygen ratio that everyone talks about. These ratios are so very high, it's very difficult to describe them with classical stellar models. GNZ11 is one of them, CS1019, and the bigger focus here is this GS3073, where the N over O ratio is 0.46. So this is orders of magnitude above what Sun has. So the question is, what produces that? I asked this question, and many other people in the field tried to answer this. We played with the IMF as much as we could. We took low mass stars, massive stars, up to 120 solar masses. We tried to vary the metallicity. Essentially, we threw the whole kitchen sink at the problem to see if there's a combination of stars that can produce this elevated N over O ratios. And we couldn't find any model, really. There's no single model that can explain such high nitrogen over oxygen ratios. Even in case of these two galaxies, it's quite difficult. So I guess the hypothesis today really is that I think if these supermassive stars exist, we can show just from the stellar evolution models that we can absolutely produce these ratios. And the scenario is, again, fairly simple if we're okay with the mass being crazy, and I'll tell you what the mass is in a second. All you have is a star that accretes during the pre-main sequence, a little bit during the main sequence. These are population 3 stars, so the mass they lose, we think, is mainly via pulsational instabilities in the outer envelope. Very small amount of mass is ejected. Most of the mass of the star actually collapses into a black hole. This is what gives you the heavy seed that people have spoken about for 60 years now, like I said. And the mass that is ejected is the one that's creating this nitrogen-rich signature. So what does a star like this looks like? So sorry, I might lose a lot of you here when I put a 7,000 solar mass star here. This could be 1,000 or a 10,000 if it helps you a little bit. But I'm just going to show you basic stellar evolution calculations. On the left-hand side, you'll see the HR diagram, so the surface properties of the star. And here you're going to see the internal structure of the star, the Kippenhahn diagram. So here in the HR diagram, I've marked some zones here, 1, 2, and 3. This is the pre-main sequence evolution here. 2 is the contraction to the main sequence and hydrogen burning. And this 3 zone here is where the advanced nuclear burning stages occur. In the Kippenhahn diagram here, you see this region here, purple zone, is the convective region of a star. This is the radiative zone, and certain energy nuclear burning zones are marked here. So I'm going to take you over the evolution of this star and to show you what is the mechanism of producing this nitrogen. So starting in the pre-main sequence, you can see very quickly after a very short phase that lasts a few hundred years or so, the star essentially gains most of its mass along the Hayashi line. So this is very much a red supergiant protostar, as it were. It evolves along the Hayashi line, and the internal structure of a star is fairly basic. You have an extended radiative region in the star, and on the surface, because you have accretion onto the surface, there is this convective zone that forms. This is deuterium burning that's occurring in the star, and as we know, it's quite inconsequential to the stellar structure. The star is essentially contracting at this point. But once the star is done accreting this mass, and it has gained, in this case, 7,000 solar masses or so, all the matter available to accrete has now gone away. The star must contract to the main sequence. And that's what it does here. Here you see the star coming along the Hayashi line, accretion terminates, it contracts to the zero-age main sequence, and then this is the central mass fraction of hydrogen here, meaning the star now begins to burn hydrogen. Now, in the Kippenhahn diagram here, if you were to just squint and look at just the left part of this plot here, dare I say this is a classical massive star, right? You won't disagree with me on this one. It has a convective core that is receding in mass. This is core hydrogen burning zone, and has a radiative zone. And as convective core recedes, as it's burning hydrogen, the star begins to expand towards the Hayashi limit. A classical convective core radiative envelope massive star. But things start to get interesting, as it does for classical massive stars, when they reach the Hayashi line, as in they become red supergiant stars. Here, this is a red, super giant star. And we'll look at the advanced nuclear burning phases here. So just this plot shows you the HR diagram. This is phase 3. Most of the time it spends here sitting on a much cooler temperature. But the structure now has changed drastically. It's begun to change a lot where most of the star is convective with some intermediate convective zones here. This is core helium burning region here. Again, the convective core that's receding. This is the convective hydrogen burning shell. So this I can explain in a slightly, my attempt to be cool to make fancy plots and compare to the 3D simulation. This is a POP3 star, a supermassive star at the start of core helium burning. This zone here is the convective helium core. On top of that, this thin layer is the hydrogen burning shell. You have another extended convective zone, convective radiative intermediate zone, and then another large convective zone on top. So essentially the star is slowly turning into fully convective. And I'm going to show you something very simple and most of you would recognize immediately. All that's happening in this star is that in the core of this helium core of the star, you're fusing helium and you're converting it into carbon. You transport this carbon to the hydrogen burning shell, and there this carbon simply fuses with hydrogen to produce nitrogen. If this sounds familiar, it really should, because it's nothing but CNO cycle, right? So nothing fancy is happening here. But because the star is almost fully convective, it is very efficient at transporting elements. Here, I'm not talking about rotation. I'm not talking about Taylor-Schwaite dynamo. It's just the convective nature of the star that's transporting nitrogen and, well, all the other elements as well that it's producing. A more scientific plot perhaps here. This is now the end of the lifetime of a star. So we've pushed these models until the end of core silicon burning, meaning a minute, a few seconds before the collapse of the star. These purple zones indicate the convective zone, and these white zones here are the radiative zones. Again, this is the mass, this will be the center, this is the surface. And you see, because of this strong mixing, which simply occurs from convection and nothing else, you transport helium, or you enrich helium strongest at the surface. This is at the expense of hydrogen, which is the second most abundant element. And then you have simply nitrogen, oxygen, and carbon. And the structure of the star, you see, is almost fully convective. So if I were to then take the stellar yield of this star, and put it and take the ratios like how everyone does to determine what the N over O ratio is. And if I were to put it in a plot like this, oops, definitely not that one. This is GS3073, that target I spoke of. You see these stars, these individual stellar models, so I'm not talking about a population, I'm just talking about a single object, can reproduce the nitrogen over oxygen ratio. Not only can they reproduce, but they overproduce nitrogen, which is important because you'd imagine these are POP3 stars. Once they die, next generation of star forms, they would have much less nitrogen yields, so the N over O ratio has to go down. So it's important to overproduce this. But on top of that, we can also do the same for carbon over oxygen ratios and also for neon over oxygen. And please bear in mind that because these are supermassive stars, we're also reproducing the heavy seed to begin with. So we're explaining the black hole mass, and we're also explaining all these abundances. So this, to me, or if you believe it or not, would be, we think, is the first evidence where we can reproduce these abundances using a single supermassive star. The other thing, since I have a few minutes, half a minute or so, I'll also quickly highlight. So Professor Loeb asked me what the atmosphere of such a star would look like. I had no idea at the time. So our idea was to now explore, hey, what would be how these stars we know are super, they have very large radii. What kind of atmospheric properties would it have? So essentially what I'm showing you here is that this opacity bump that occurs like in most stellar structure where you have this small convective zone. This is the region where all the lines, if such a star were to exist and you were to look at this star, you'd be able to see line features coming from here. This is, look at this crazy number of luminosity, by the way. These are some of the stellar models where I tried to develop a spectra of these stars to show what they look like. And really building on the talk that Anna de Graaf gave 2 days ago, she thinks it's for LRDs, it's these black hole stars, as she called them, quasi-stars. I think these are supermassive stars where if I were to then take this spectra and put it on top of these targets like this MOMBH1, these LRDs, or the Cliff target, these supermassive stars can reproduce this H-beta feature here, and also the profile of this the continuum. So do we think all LRDs are supermassive stars? Absolutely not. But if these stars were to exist, then, I don't know, 1 out of 1,000, 1 out of 1,000,000, supermassive stars would be a perfect, or LRDs would be a perfect environment for these stars to hide in. These are super bloated, red, no X-ray signatures, hydrogen and helium line features. that'll be LRDs for you. So this is my summary slide. Sorry, I've overstayed my welcome. In case you're still wondering how massive can they truly get, that's the answer. So, yeah.
So Devesh, there were some very massive black holes inferred from LIGO. Do you think they are, what kind of progenitors do you need to make them?
So, yeah, so 100 solar mass, we had this talk a little while ago where a researcher was showing about 100 solar mass, 130 solar mass black holes. The problem there, of course, is, the redshift was also enough where these can't be from the solar metallicity-ish stars. So this metallicity is slightly lower than solar. The problem there, as you know, is about this parent stability gap. So classical, again, unless there was a merger that led to this 100 or 130 solar mass stars, if you want to produce it from a single seed, actually you would need a star that is at least 500-600 solar masses, all the way up to 100, well, I've checked this, 1,300 or 1,400 solar masses. So if you were to take this star, it undergoes mass loss. If we calculate the remnant size of this, then that's how you would be creating this SMS seed, unless it comes from a merger, which could be another scenario, I think.
Colliding and
yes.
producing such.
So I have some results on that. I'll be putting that out. Yeah, exactly. So we study the growth of these stars via collisions as well. Like what is, yeah. But yeah.
Any final comments, please?
So I guess you bring the nitrogen out by mass loss by wind. So how much do you think is like well understood about these mass losses?
Absolutely. The answer is not much at all. You know, mass loss for population 3 stars is already very difficult. I hope I kept this slide for once. No, maybe I can show, maybe this would be a better way to show. Yeah, so supermassive stars are somewhat agnostic to how the mass loss should occur, if the mass loss has to happen, simply because the star is mostly convective. You know, no matter where you take a slice out from this star, whether you lose 1% of the mass or 50% of the mass or something, because the star is mostly convective, the ratios for most part do not change at all. So yeah, to give you an answer, we don't know how the mass loss should occur. These are objects close to the Eddington limit, and you cannot say how do they form in the first place if they are close to Eddington, but there should be Eddington limited mass loss, there should be pulsational mass loss due to epsilon mechanism, and there's also this strange mode pulsations that they say. But to give you an answer, no one knows how they lose mass or how much.
Yeah.